All right. Okay, our next speaker is Marcus Hultmark from Princeton University.
Thank you. Thank you for inviting me to come and talk here. I didn't really know what to talk about, so I decided to talk about a little bit of everything.
Rich didn't tell you what to talk about?
Well, I'll next time I'll tell you what they told me, and then what I decided to talk about. So anyway, I'll talk about instrumentation and measurements in general in high Reynolds number flows. And okay. Oh. There we go. No. Okay. All right. So basically, some of the research areas in my lab involve wind turbines. Here's some atmospheric boundary layer fluxes. We do unsteady aerodynamics, some drag reduction based on sort of bio-inspired surfaces. Here is a supersonic, really a supersonic sensor here, but we're doing supersonic boundary layers. This is a mosquito, which is interesting. I'll tell you about that in a second. And this is just supposed to represent turbulence in general, and then the little Swedish flag there. So it was called Beyond the Boundaries, right? So I wasn't really sure what to talk about, so I decided to talk about nothing of this. Instead of talking about instrumentation that sort of links all of these problems. So all of these problems actually are affected by turbulent boundary layers. I think most of them are maybe fairly obvious, turbulent drag reduction, turbulent boundary layers, but you might ask, like, how is this possibly turbulent boundary layers? And well, the boundary layers on the wings are not turbulent, but they are living in a turbulent boundary layer. They are orienting themselves and they are sort of feeding in a turbulent boundary layer. So it turns out that the structures in the turbulent boundary layer are very important for mosquitoes. So anyway, what I was going to talk about now actually is instrumentation. So one thing that is true for these sort of all of the flows, all of the situations I showed before, is that they are at high Reynolds numbers. So in our lab, we do mostly laboratory studies. There are some field experiments. I'll talk about them too, but mostly laboratory studies, and we want to do lab studies at high Reynolds numbers. So one challenge when it comes to Reynolds numbers is that this is an exact relationship in the wall-bounded flows if you think about RE tau, but essentially the Reynolds numbers mean a ratio between the large scales, could be the boundary layer thickness, and the small scales could be the viscous length scales. And if you want to squeeze this into a lab at high Reynolds numbers, it means that the large scales are limited. They're going to be limited by whatever facility you have. They're going to be limited by the lab. They're limited by how much money you have. So if you want to do a high Reynolds numbers, you will end up with small length scales. That's sort of the unfortunate fact with high Reynolds number investigations in a lab. So at Princeton, we have this facility. Most of you probably have seen data from this facility. It's the Superpipe. So we achieve high Reynolds numbers without very large length scales. This facility only has 5 inches of diameter, whatever that is in real units. But we pressurize it to 220 atmospheres. So that means that we're changing the density. So we're squeezing, basically minimizing the world inside it. Now we can get really high Reynolds numbers. Actually, the highest Reynolds number we can achieve here is RED of 35 million, or RE tau on the order of 10 to the 6. It's slightly below 1 million. So really massive Reynolds numbers. At one point, I actually got asked to review a paper where they had sort of summarized all the facilities in the world and put them in sort of what Reynolds numbers they were on. And the Superpipe came out highest of all, yet I had to point out that they were 1 order of magnitude off. So it's really one order of magnitude higher than any of the other high Reynolds number facilities out there. Okay, so that's great until you realize that because we squeezed the world down so much, you're going to end up with really, really small length scales. Komagoro length scales in this facility at the highest Reynolds number is less than a micron. So that's pretty darn small. So if you want to measure turbulence, you want to see all the details, you really limit it to 150,000 or so with conventional sensors of RED. 3,000. That's unfortunate. You build a facility that is good for 35 million, but you can only run it to 150,000 with full resolution with conventional sensors. Now, it was used before the research I'll talk about today with the novel instrumentation, but it was mostly used for mean measurements, mean velocity measurements, which are less affected by spatial filtering. Okay, so here's a quick outline of what I'm going to talk about. Basically, lots of different sensors. I'll talk about hot wire anemometry. So how do we use hot wire anemometry in this facility or in any other high Reynolds number facility where we really need high spatial resolution? I'll present the NSTAP and a couple of versions of it. And then I'm also going to tell you about a cold wire version of this same sensor, basically for temperature measurements. And then I'm going to flip it upside down and say these turn out to be very useful in field studies, which makes no sense because the whole idea was that the large scales were constrained. So we end up with small scales. But it turns out that another feature of these sensors, which is the time response, is very convenient when you do field experiments. So I'll tell you a little bit about that. And then I'm just going to show something that I think is cool for the future, another sort of feature and a benefit of pressurized testing. So, all right. So most of you probably know how hot wire works, but I'm going to just tell you one more time. A hot wire is a wire that is hot. So there's a little wire that we heat up with an electric current. It gets hot, and then we measure somehow, we correlate the heat transfer to the velocity. It could be done in different ways. It could be constant current, constant temperature, but the idea is the same, that we're trying to correlate the heat transfer to velocity. It can be fairly fast, on the order of 50 kilohertz or so. It's not quite clear exactly what the time response is. Depends on the flow. This is with feedback. So if you don't have feedback on a hot wire, it's much slower. It's on the order of a couple hundred hertz or so. It's relatively small, so 0.5 millimeter is small compared to sort of the size of the Earth. It is very large compared to the micron scaled Kolmogorov scales we had in the Superpipe, right? So this was the motivation. How do we make a hot wire smaller? It's sort of limited to this. Maybe you can do a little bit smaller than that, but the conventional way is you do it by hand, and it gets really challenging to make things much smaller than this. And here's the reason. If you want to see the smallest details, as you pressurize the world or as you increase the Reynolds number, you're going to miss all these details. So what's going to happen is that you're going to bias your data in ways that are some effects of bias might be obvious and you can correct for. Some are not as easy. So there are two kinds of filtering effects you will end up with. Spatial filtering effect is the one I just showed you, where essentially your wire is longer than the details of the flow, and you will basically not see those details. The other one is time. So you can somehow you're measuring the heat transfer. There will be a thermal inertia involved, even if it's a feedback loop. And if things are changing faster in time than the wire can respond to, you will not see them. I would say in subsonic turbulent investigation, spatial filtering is typically more limiting than temporal filtering. In supersonic, it is typically the opposite. But the fact is that most likely, if you do high Reynolds numbers, you end up with both of these two effects on top of each other, and it's not quite clear sort of what's going on. But this is data by Nick Hutchins, where he measured the same boundary layer, same Reynolds number, same distance from the leading edge, same everything. The only difference is the length of a wire, which means that this is the shortest one, this is the longest one, and you can see that the variance profile here, non-dimensionals and in units, really looks quite different. So if you're trying to distinguish trends or absolute behavior of these curves, you will introduce bias by the spatial filtering. And if you're trying to understand how things behave with Reynolds number, that bias becomes even worse, because now the length, that the governing parameter is not the length itself, it's the length over some some length to the flow, which is decreasing with Reynolds number typically if you're in the same facility. So therefore, you can literally just bias and put in trends that are not there. Okay, so this was a while ago now, 2007 or so. It was proposed that we should just use sort of the modern tools in the clean room to make really small sensors. So just take the wire that typically is welded or soldered on by hand and make it smaller. One problem is that you need to make sure that the cross section is sort of small compared to the area that the flow sees to reduce end conduction effects. So what you have to do is you have to reduce the cross section in order to shorten the length. And in a clean room, you can do really fantastic things. So this was one of the first sort of designs. Clearly, it's not the real design, but where we have a thin layer of platinum on a freestanding silicon structure with a little wire exposed. And the wire the thickness of this layer is typically 100 nanometers. That's what we typically use. We can play around with that. 100 nanometers is a pretty convenient number because it's sort of large compared to molecules and small compared to most other things. And here's one of the earlier versions of the end step. So it uses, the good thing is that it uses advanced tools, but well-established tools. So we didn't have to invent these steps. We just had to follow what people have done before, and then we can create these structures. And here is the end step. And you can, this is, I think this is a 60 micron one. And you can compare it to a regular 1 millimeter one in the scaly ratio. Okay, here's another picture of it. This is a fairly early picture. We have gotten a little bit better at making them, but basically you can see the platinum here. You see a wire. You see the silicon, and you can use this just as a regular hot wire. You lead a current. You'll heat it up, and you can relate the heat transfer to the velocity. Now, of course, the thermal mass of this small wire is much smaller than the thermal mass of a conventional hot wire. So not only is it smaller, so improved spatial resolution, but you will also improve how fast you can adapt to changes. So the temporal response is also better. So what we did was that we have the Superpipe. We decided to test, and I'm not going to go into too much into the details, but basically now we could surpass the 150,000 that was limiting before, and now maybe somewhere around 3 or 4 million is really where we should have stopped. While we push a little further, the resolution isn't amazing here, but it's sort of okay. We should have pushed a little bit more. This is sort of annoying that it was 98,000 and not 100,000. But it's on the order of 100,000, I guess. And what we could see from this is now the same as shown before, the variances, non-dimensionalized and inner units, with u tau and plotted in outer coordinates. We could see here as the red is the highest Reynolds number, that there was a logarithmic dependence that sort of appeared in the variance profile. And I should point out that this kind of behavior will be highly biased by spatial filtering, right? Because it will be pulling this down, and it would not look like a straight line in this plot, but instead would look like this. So we were able to see this logarithmic behavior, and it was really due to these, well, first the facility that can allow us to test at 100,000, but also the small sensors. So it turns out that this logarithmic behavior occurs at the same place in space as we have the logarithmic behavior in the mean flow. And one could ask, what does it change in a boundary layer? After all, this is a boundary layer workshop where it's beyond the boundary layer. So I guess pipes are beyond boundaries. But we could just put we happen to have a facility right next to the Superpipe, which is the high Reynolds number test facility, which is a wind tunnel. So it's not a pipe flow, even though it's a pipe. It's a wind tunnel that has a flat plate in it and behaves just like a wind tunnel, but also pressurized up to 220 bar. And we can get 75,000 RE tau. So pretty high, not as high as the Superpipe. And we can go in and we can measure, and we see the same kind of behavior. And this line is the coefficients for these lines are from the Superpipe. All right. Now it turns out that people had certainly talked about this many decades before we took this data, and I would say this was one of the first, at least when it was really sort of consistently shown because of the high Reynolds numbers, that it was this. And then Ivan and others have seen it also in boundary layers. You really need sort of an RA tau of 20,000 or so to really see this extended log layer. But one thing I want to point out is that Townsend and Perry's work both sort of gave a k to the -1 behavior in the spectra, and then that in turn gave the logarithmic dependence. But one surprising thing, at least to us, was that we did not see a k to the -1 behavior. So here is the lower Reynolds number, higher, and the highest Reynolds number. And if you had a k to the -1 behavior, you would have a flat line here. And you can see at the lower Reynolds number, it's sort of, I don't know if it looks flat, but it looks more flat than it does here. So for some reason, we see the result, which is the logarithmic behavior, but we don't see the k to the -1 behavior. And I think the jury is still out on exactly how we can link these theories to the observations. Okay, so I just want to talk more about instrumentation. Now, most data that we have from turbulent boundary layers are for the streamwise component. And I would say that is most likely because that's what we are the best at measuring. But the most important component is really the wall normal one, because that's what brings the fluxes of momentum, fluxes of heat, fluxes of water vapor. So to do that, we need a crossed wire. And we had this brilliant idea. Why don't we just make two asymmetric end steps? We just tape them together. This is it's not just tape. It's an ultra smooth Kapton film with gold spotted on it, and we put them together and we just bond them. And then if you do that, you end up with a cross like this. Okay, so you might look at this picture and say, oh, that's pretty cool. There's a cross, but it's really bulky, right? So you have the end step itself is a little on the bulky side, I would say. And if you put two bulky things right next to each other, it gets even bulkier. So we were worried about this. We were trying to see how it behaved with angles. So a cross wire should follow this line and that line, and it's fairly okay up and down like this, but it should be flat when you go the other way. And it is not. This is a cross wire. This is a regular end step. The regular end step is maybe okay here, 3 or 4% to plus minus 15 degrees. The new cross wire was pretty bad. So what we did was that we said, okay, well, let's try to understand what's going on. So first we made the smallest sensor that was out there, and then we 3D printed a really large version of it. So we 3D printed a version that was 250 times bigger than a regular end step. We put it in a water tank at the matching Reynolds number to understand what's going on with the streamlines. And you can see here that this streamline is coming in, and it's being really disturbed by the structure, right? So the answer is, okay, we need to make a thinner version. Here is the original one. You can see the green streamline coming in. And here is now a thinner one. Basically, we just 3D printed until it looked good. And then we said, how do we make this? And it turns out that we cannot make it in silicon anymore. So we had to put on very thin tungsten sort of prongs. And so now we have silicon and tungsten and then platinum. And the tungsten is holding it. And here's the new version. So now we can look at how it behaves. And it behaves as good or actually better than the original single wire end step. And we can take data, and it looks fairly promising. It follows the DNS pretty well. There's still work to be done. This wire is a pain to deal with because for some reason there's always something breaking, but not the wires, it's everything else. Okay, so because I just want to talk about sensors today, I'm skipping all the data, and we can talk about it over beer later. But one thing that we wanted to understand is how fast is this sensor? How can we make it faster? This is for supersonic measurements. This is together with Pierre Dupont and Diogo Barros at Marseille. And one thing that we basically just exposed it to step waves like this is a nice of constant current. It's a nice first order system. We can fit the first order curve here. And what we thought was that, well, you have a small wire here. There will be some heating here as well. Thanks. So what if we reduce the heating by putting gold on here? So we reduce the resistivity of the sort of holders. So we get more of the heating localized to the sensor. And you can see this is a conventional hot wire, a Dantec wire. This is the response time. This is the end step I showed you before. This is with 200 nanometer of gold, and this is with 320 nanometers of gold. And we actually can improve the response time by a factor of 10 above the end step. So the reason why we wanted to do this is because we would like to operate in constant current without feedback. And it's not published yet, but basically we get 100 kilohertz response without feedback with this system in a supersonic. And there's another cool thing here too. If we look at these time responses for the regular wire, they change. This is with the overheat ratio, but they sort of change with the flow. Whereas the end step, especially the one with gold, seems to be dead flat whatever we do, which is really good if you want to use this to compensate, so some kind of numeric compensation afterwards. All right, so now we're going to switch, because we did all this for supersonic measurements, but it turns out that it's really convenient in the boundary layer, the atmospheric boundary layer. If you do field experiments, you might say you want to have 100 sensors somehow distributed in your boundary layer measure. If you were to go to Dantec and say, give me a quote for 100 sensors, they would happily give you a quote, but it will be a couple of $100,000, if not more. And with constant current, you can build a circuit yourself. There's no feedback. It's very easy. These sensors are really small. Small is good when it comes to semiconductors. They cost roughly $1 a pop. So you can instrument the heck out of a facility like this. And that's what we did. And I just want to show, here's some data. This is for temperature. This is for velocity. And this, by the way, here is the -1 behavior. So in the field, in the atmospheric boundary layer, K to the -1 is very prevalent. You see it almost always when you get sort of high quality turbulence data. In the lab, for some reason, it's much harder to see it. So this could be a Reynolds number thing, or it could be something else. Okay. I'm not going to talk too much about temperature sensors. It's like the same thing. They're just even more important to get the timescales right, because now you're really racing and lowering the temperature completely by the flow itself, right? Okay, that's the temperature one. So I said, okay, 2 unexpected outcomes from this turbulence research is something completely non-turbulent. So there are 2 startup companies. Instruments spun out to commercialize the NSTAP, and they're working with sort of medical devices in Silicon Valley. I think they're having fun. Don't really know what they're doing. And then Tender Technologies is another company that spun out to commercialize a version of the NSTAP, which is based on strain. So we actually measuring the strain in the wire instead of the heat transfer. And that is being used for liquid dispensing of really small volumes. So completely different from what it was originally designed for. And this is together with L'Oreal and Pepsi and another large company that I can't mention right now. Okay. Okay, so because we probably have like 2 minutes left, I want to show one cool thing about pressure. So pressure is good to get high Reynolds numbers, but even better if you want to do unsteady turbulence measurements at high Reynolds numbers. So this is just a wind turbine. I'm showing this because it has a time scale that is imposed by the system. So if you have that, you end up with 2 non-dimensional parameters. The Reynolds number still stays the same, but you have now a non-dimensional frequency. This could be any kind of flow. It could be aerodynamics, could be just a turbulent flow that's doing something. Now, because the velocity is here in the Reynolds number and there in the non-dimensional frequency, when you scale this down, if you want to scale things down, you end up with, first you have to increase, typically you have to increase the velocity to change the Reynolds number. when you do that, you have to increase the frequency with the square of the scaling ratio, because you have the scaling ratio here and then again here. So for a wind turbine, this turns out to be impossible. But if we do this with pressure instead, now you can scale down your length scale. You can increase the density. You don't have to increase the velocity, which means that you only get a linear proportion on the frequency. So now you can test, for example, in the wind turbine, instead of 400,000 RPM, you get 7,000 RPM. But this translates to any kind of unsteady turbine flow. And we are doing this in the HRTF, as I showed you before. And I want to show you. So I showed this. Some of you might have seen this before. I've been talking about it for some years. This is the super tank, we call it. So if it was atmospheric, it would be, you would have to have 1 kilometer long facility to get the same Reynolds number as you get in this facility. This is only 12 meters at 90 bar, and here it houses a wind tunnel inside it. So we get really high Reynolds numbers, and it's built. It's sitting in China. We're waiting for it. We've been waiting for it for a quarter of a decade. We've had, basically, I'm happy to talk about this over a couple of beers later, but if you have a project where everything goes wrong, that could possibly go wrong, this is it. But I'm a hopeless optimist, so I'm thinking that it probably is going to come now in June or so. So, yeah. Anyway, conclusions: turbines, cool. Pressure is good, and small sensors make life easier.
Great. Thank you very much. A couple minutes for questions. Martin?
Yeah, thank you, Marcus, for the nice talk. I have a quick question related to the pressurized facilities. What would be the Kolmogorov-based Knudsen number for either the Superpipe or that new facility? Could you estimate that?
I mean, Knudsen number, you end up being, the compression helps you, right? So you're not going into some kind of the continuum approximation is very good, because you're pressurizing it the same amount as you're actually scaling up. I'm not sure if it's going to be very close to a linear relationship. It's actually the opposite might be the more of a problem. If you pressurize it too much, the molecule get too close, and you end up with other kinds of forces. But we're in the range where that doesn't happen.
Hi, Marcus. I could ask you a little bit about the K to the -1. You said it could either be higher Reynolds numbers or something else.
Oh, in the boundary layer, in the atmospheric boundary layer?
Yeah, I just wondered what the other things could be.
Yeah, I mean, that's a great question. So the other things, I mean, I think it's a Reynolds number. That's my guess. But there could also be, in an atmospheric boundary layer, you might have instances of neutral conditions, but the history is never neutral. There's always stability going on before and after. So there could be other reasons for it. I'm just saying that it is not as well controlled as, yeah. I mean, it could be transients of so many. Basically, in the ABL, there are transients of everything, pretty much, right? So we are identifying some stable conditions based on what's going on right now, but what happened before and what happens later could be. So it could be buoyancy, but I think that it's Reynolds number, because whatever you do, we always end up seeing them really convincing K to the -1. Now, well, no, it doesn't actually. So I was picking which graph should I show this morning, and it does not look this convincing. If you show a log plot from the Superpipe, you would not have this. Yeah, I mean, basically, I guess you mean you need to stretch it out even more. Like,
the point is that the spectrum turns over.
Yeah.
There's always a tangent point, but I think your point is it's more than a tangent point.
Yeah, I mean,
It needs to pre-multiply and so on.
yes.
And your plateau is 0.95.
That would be, yeah.
It's pretty close to what we find if you
Yeah, if you, yeah, I mean,
Separate out the effects and what the true case
Yeah.
is. Anyway, we can make this a good topic for discussion.
Yeah, with that, let's save other questions about k to the -1 for the discussion and thank Marcus one more time for a very
you.
nice talk.